Hey guys, so I thought I'd do something a bit differently today. I thought I'd include some of me actually speaking. Maybe it'll make it feel a little bit more like a lesson and might make things a little bit easier to follow along. If it's distracting though, let me know and we can always change back to normal. So, last time I saw you, we were talking through different things to do with sine rule and cosine rule, and really just using those to try and solve as many problems as possible. This is really where the sine rule and cosine rule is finished now. We'll be looking now at things to do with the sine graph, the cosine graph, the tangent graph, and really their transformations. So I'm going to talk you through the three different graphs that we have to begin with, and we're going to point out all of the key features that we would need to know about these. Now, these key features are things that you need to know off by heart. They need to be fully memorized. You need to be able to imagine this graph in your head. So I'm going to talk you through the things that I know about this graph, kind of in the way that they make the most sense to me. So the first thing that I think of when I think of the sine graph is I know that it starts at the origin, and I know it's got this characteristic shape of the kind of wave up, and then I know it's got the characteristic shape of the wave going down as well. I also know that that full period, which means how often it repeats, is every 360 degrees. Some people think that it repeats every 180, but actually if it repeated every 180, it would have to be the same pattern every 180. It would be these kind of bumps instead. So the up and down wave is every 360 degrees, and it starts from 0. Something else that I want to point out about the sine graph is that it has got the symmetry that you would expect it to have. So when you look at this part of the graph that we've got here, because it's between 0 and 180, 90 is obviously going to be bang in the middle. You need to have that memorized, that sine of 90 is going to be where it has this peak. And again, between the 180 and the 360, that 270, which is halfway between 180 and 160, is where it has that trough. And a trough just means sort of the opposite of a peak, where something has the lowest point that it might be. The other thing that we should notice here is that the range is really just referring to the y-axis. The range of the sine graph is between -1 and 1. So let's just add in some of these bits that we've got here. We can clearly see that the maximum value of it is 1, and that's when it is at 90 degrees. We have that the minimum value of it is at 270, and that gives you a minimum value of -1. Now, the sine graph, and we'll explain this why in the future, actually repeats itself. It doesn't just have this section of the graph. And actually, the thing that really is kind of weird is that you can even have angles that are bigger than 180 and that are smaller than 0. Because if you imagine where the definitions of sine, cos and tan came from, they came from right-angled triangles. So in a few lessons' time, I'm going to explain to you why you can go beyond this sort of first bump that you have here, and actually why it makes sense to be able to go further than these ranges. So because it repeats itself, you can see that if you go backwards, you can also have the same happen as well. Another sort of S-shaped curve that you've got like this. So key things I think of when I try and memorize this is it starts at 0 and it just goes up first, then down, and it's 360 degrees. You need to be able to memorize that shape in your head. So I'm going to have a think now about trying to see if we can solve some additional things about this graph. So it says here, suppose we know that the sine of 30 is equal to 0.5. So let's just quickly break this down a second. The sine of 30, that is saying that you're putting 30 degrees in the x-axis. So I'm just going to go back over here. I'm just going to notice that this is the x value that we're putting inside the sine graph. The y value that it gives us is 0.5. And it says, by thinking about the symmetry of the graph, how could you work out these three other things that we've got here? So, I'm going to draw in the lines that I've got, if I can find my shape tool. I think it's perhaps disappeared on here. I can do it with a straight line by hand anyway. Okay, so we're saying that at 30 degrees, it has a value of 0.5. So let's have a look. Here is 30 degrees, and the y value is 0.5. Now, if you look across, there are going to be some other values at 0.5. We can see some other x values that will correspond to that, okay? So if I just go dot it all the way along here as well, this is why I wish I had the straight line tool, which has disappeared from my toolbox. you can see that there's some other x values that are also going to give you that level of y value as you go across. So let's have a quick look. One of them is at 30. Now, if we want to try and find out what the sine of 150 is, well, 150 is about here. And what we should notice is that this gap, which is 30 degrees, should be the same gap as this bit here of 30 degrees, because that first hump here is symmetrical. So if this red line that I've drawn is 30 degrees, then this red line would be 30 degrees, meaning that the angle at this place here is 150. So the sine of 150 is indeed 0.5 as well. Now, we know that actually from earlier on, because if you go back to some of our slides when we looked at the ambiguous case, which I've got here, we said that you get two possible solutions for the angle. You get sine of theta and 180 minus theta. And we talked about that with the graph, that when you had this distance here, you could come back that same distance for 180. Coming back, meaning 180 subtract. So let's scroll down back to where we were here. Now we're going to see if we can figure out some of these values. So this next one is the sine of minus 30. So minus 30 is going to be on this side that we have over here. And we're trying to find out what the y value would be. So let's just go down from the 30 to try and meet the graph, and we're going to try and predict what this value here should be. Well, we know because it's got rotational symmetry, that means that if you were to rotate the graph about the origin, it would land back on top of itself. If this value up here is 0.5 for 30, we can see that when we come back across to minus 30, it will be on the negative side of the axis, and it will be at minus 0.5. So the sine of negative 30 is minus 0.5. Now, let's see if we can use that idea to help us find out what 210 is. Now, 210, you should recognise that that number is related to 180, and it's 30 bigger than 180. So this first piece of information about this section of it corresponding to going 0.5 up is going to be the same for over here. So when I say I'm going to go along to 210, that means I'm going to be coming down to the graph, and because it's also got this idea of 30 degrees, it's going to correspond to this same negative value that we have over here of negative 0.5. So using these symmetrical properties, when I say the symmetrical properties, I mean recognizing we can go 30 in this direction and 30 back from 180 or 30 forward. It's always from these these points down here at the bottom that help you figure out what these extra values are going to be. So that's what we're going to have a look at for some of those questions in just a second. So we're going to do the cosine graph as well. Now, the cosine graph has got lots of features that are really, really similar. It's got the same idea that it repeats every 360 degrees. Oh, that's the wrong range that it's got written there. It says sine. Let's change that on my pen. Let's change that so it's the correct one. It should say, it's the same range, but it should have just said cos. And it still goes between -1 and 1. You can see here you've got the peak of 1 and you've got the lower bit down here of -1. The way I think of the cosine graph, it's a wave, but it starts at the peak of the wave. So I'm just going to draw out what I think of when I think of the cosine graph. It's like the sine graph, but it's kind of been shifted around. The sine graph would normally start here and do a form like this, but the cosine graph is starting at the top. And that means that when it starts at the top, it comes to the very bottom after 180 and back to the very top again after another 180, all the way up to 360. We've still got that same idea. We're going between 1 and -1, but you can see things like if you were to do the cosine of 90, you get 0. And cosine of 180, you get -1. Cosine of 0 being equal to 1. You can now be able to think, if I say to you, oh, what's the cosine of 0? You should be able to tell me that it's 1, because you should be able to visualize this graph. So sine graph, you should think about it starting at 0. Cosine graph, you should think about it starting at 1 and doing that pattern. It still repeats itself as well, so it comes backwards like this. But what you should notice is that the cosine graph is completely symmetrical about the y-axis. It's almost like this part is completely flipped onto this part, whereas the sine graph doesn't have that kind of symmetry. It has a rotational symmetry where if you imagine this bit spinning around 180 degrees, it would be true. but it doesn't have this kind of symmetrical, like mirror reflection that you would have down the middle, like the cosine graph does, like this. We're going to do a similar thing now, and we're going to try and find some additional values from the cosine graph. So they've now said, suppose we know that the cosine of 60 is 0.5, and this is true, obviously, you can check that on your calculator. By thinking about symmetry in the graph, how could we work out the cosine of 120? So I'm going to go back to here. Let's see if actually I'm going to put it in Tues for a straight line because that would be really helpful. I don't know where they are. I'll see if I can find them next time. So what we're going to do is we'll put on the cosine of 60. Now 60 is going to be a bit further along. It's going to be a bit closer here. And there it is, reaching up, and it meets at our 0.5 that we've got here. Now we know that this distance is 60 degrees. This blue distance here is 60 degrees. Now we're going to try and find out what the cosine of 120 is. Well, it looks like 120 is related to 180, but it's gone backwards 60 degrees from the 180. So if we've gone backwards 60 degrees here, noticing how I can only really draw on the 60 degrees from these points where there's some symmetry. If we've gone backwards 60 degrees, we go to 120 and we look down to the graph, we should see that this is going to correspond to a negative value. But if you think about how 60 degrees in this direction from the peak downwards and then from the trough going upwards, this should also be at the minus 0.5. So this gap that it's risen from here to here is 0.5, just like this gap that it's fallen from here to here is 0.5. So the cosine of 120 is minus 0.5. Obviously you could type these things in your calculator, but the whole point of this is we're trying to look at the properties of the graph.
So the cosine of minus 60, that means you're taking the x, the x coordinate is negative 60, and we're going to try and find out what the y part is. So I only know something about this gap, so I'm going to draw out a gap of 60, and here is where 60 would be, so minus 60. Now if you look up to the graph, we can see it's going to correspond to the same value as the cosine of 60. So the cosine of 60 and the cosine of minus 60 are both 0.5. Now I guess the reason we can see that that's true is because we've just said that it's symmetrical about its axis. So if you're at 60 degrees this way, if the sine is going 60 degrees this way, because of this line of symmetry that we have going down the middle here. Okay, let's have a go about the cosine of 240. So
240, we want to try and think about how is 240 and 60 related to some of these key values that we've got here. Well, if we think about 180 and you add on a gap of 60, we couldn't add on the gap of 60 to any random value. It's either got to go to the 180 or to the 0 part here. We want to see how that's going to play out. So I'm going to go to the 180. I'm going to add on a 60. So again, I'm just still drawing on that same amount of line. And that's going to take me up to 240. And I know for this kind of gap, when it comes down here, we know that from 180 going 60 backwards, it gave me negative 0.5. So because it's symmetrical and this is the peak of it, sorry, the trough of it, when I go 60 in this direction, it's also going to give me that same value of minus 0.5, okay? Now, I've just happened to pick ones that have got nice values, like 0.5, and the previous one also had a 0.5. But this would work in a similar kind of way if it was like the cos of like 50 is equal to whatever that is on a calculator. You could still use this same idea. So let's just quickly pull both of these together for a second. You'll notice that we only did the movement from the 0 going backwards or forwards 30 degrees for the sine one, or from the 180 going backwards or forwards 30 degrees. We didn't do it from the 90 or from the 270. We did it from the 0 and the 180 that we had here. That's the same thing for the cosine. We went backwards and forwards from the 0. We also went backwards and forwards from the 180. And the first bit of information tells you how much backwards or forwards that you can go for that. So we're going to now have a look at the last graph, which is the kind of one that is a bit weirder. We will explain why this is true, why this is what the tan graph looks like. So this is, I don't think I've ever got this written here, but this should say at the top that this is the tangent graph. Because tan is actually short for tangent. So it's got this weird kind of pattern, okay? It's easier to think of it starting at 0 and it immediately kind of shoots upwards. It looks a bit like a cubic graph, but it's not a cubic graph. And it shoots so far upwards that there's actually something that we have that's called an asymptote here. This is an asymptote that we have. And an asymptote is a line that the graph approaches, but it never quite gets to. So if this graph kept on going, it would keep going up and up and up, but it would never actually touch this dotted line. Now, this is the way I kind of think about this. This line, it goes so far up here that it goes to almost infinity, 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 and it actually wraps all the way around here to like negative infinity, and it then comes up like this, and it swerves to 180, and it gets to 0, and then it does the same thing again. It keeps going way up towards positive infinity again. And then it almost like wraps around as though it's going so far up the top of the page that it actually comes out at the bottom of the page on the other side of the asymptote. Perhaps it's a bit easier to see it in this section. Like it's kind of all the way up here, it goes so far, it somehow jumps over, and it comes up on the other side like this, and comes to 180. In fact, maybe if I can just quickly go into Desmos for a second, and I might see if I can show you what this looks like in a bit more detail. So let's have a look. Let's put in a tan of x for a second. So you can see it a little bit more clearly now. You can see that it starts at 0. It's actually in a different mode. So I might see if I can just quickly put this in degrees mode. Yep, there we go. And I'll have to do the x-axis for minus 360. Don't worry about this bit just yet. I'll be telling you a bit more later on about that. And there we go. So you can see it's got that same kind of pattern. I'll see if I can mirror the same axes that we had here. Let's do it between 1 and 2 then. Minus 2 to 2. Okay, so you can see the same kind of pattern. When you get to 90 degrees, which is here, it kind of shoots all the way up. And when you zoom out now, you can get a sense of what's really happening with this tan graph. Let me just quickly put in some of these extra lines, or x equals 90. So you can see that x equals 90 is one of these asymptotes. And now you get a bit of a clearer idea of how this red line is going towards that blue line, but it never actually quite touches it. It then somehow shoots down on the other side, and it's on the other part of it, and it keeps repeating that process. So I just put in a few of these extra ones. Let's put in x equals 270. Let's put x equals minus 90 as well. You can see how we've got some of these asymptotes, and these asymptotes appear to be repeating every 180 degrees. So it's like these different sections of the tan graph kind of come up in these little, like little tunnels. This is how I kind of think of them, with this sort of swiping across. So the key features that we have here is this one repeats every 180. Just remind yourself of a second. The cosine graph goes every 360. The sine graph repeats every 360. But the tan graph repeats every 180. Now, if I repeat it every 180, you can either think about it starting from the 0 and it goes up like this, and then obviously that bit's hidden, but it goes like this. That's one of its periods. Or you might think about it as just one of this kind of periods, just sort of splitting it into those other pieces instead. So I've had mine starting at 0 and then finishing at 180. Equally, you could have it starting at minus 90 and finishing at 90 instead. When I talk about roots, remember roots are where it crosses the axes. So it's going to have a root at 0, 180, 360, minus 180, and that pattern is just going to keep happening. The range of tan, though, can be absolutely any value at all. We said with the cosine graph that the range was between minus 1 and 1. Those were the top and bottom values that it could have. Whereas for the tan graph, it can be everything. It can be anything, like if I show you back on Desmos, it can be all the way up to anything up as high as we could possibly imagine, all down to as low as we could possibly imagine. So there is any value at all that tan can take. So let's now have a quick look about some of these things. So here's one that's a little bit more interesting. We're now going to say that we know that the tan of 30 degrees is 1 over root 3. And we're going to think about the symmetry in this graph, how we might work out some of these things. So let me just quickly grab my calculator so I can just tell you what 1 over root 3 actually is as a decimal. So 1 over root 3 is 0.577. That's what 1 over root 3 is. So when I put in the tan of 30 degrees, which is going to be here, the value that it corresponds to is this 0.577, or just 1 over root 3. I'm going to write 1 over root 3 just to keep it accurate. And that's when we've got 30 here. Now we can have this same idea of, we know that this corresponds to this upwards movement of 1 root 3. So if we're going to say the tan of minus 30, well, this time we're going to be going backwards 30 degrees to get to minus 30. And I think that you can clearly see here it's going to correspond to the same gap that it's moved upwards, but it's actually going to be moving downwards this time. So it's going to be minus 1 over root 3, that's like this. So that's minus 1 over root 3. And again, we're only allowed to move backwards or forwards from the 0 or from the 180. So this time I'm going to try and find where 150 is. Well, 150, that means I'm going to be moving backwards 30 degrees from here, which ends me up at 150. And we can clearly see when I go down to the graph, it's going to correspond to that same value of the minus 1 over root 3. Do you think we could find any other values that have a positive value of 1 over root 3? So let's just make one up that actually isn't listed here. I want to find one that has got a positive value of 1 over root 3. Well, let's have a look from where you can go from 180. Okay, you could move 30 degrees to the right, which would end me up at 210, if the pen decides it wants to behave. And that is also going to correspond to that positive 1 over root 3. So actually I'm going to say here that we could do the tan of 210. That also matches with some of these things that we've got here, that it repeats every 180. So look, I've gone from tan 30, I've added on 180, and I've got 1 over root 3 that we have there. Last thing I wanted to mention about the tan graph is we talked about symmetry of these. We said that the cosine graph was symmetrical. You could put like a mirror line down here and it would have that symmetry. The tan graph does not have that symmetry. Now, the tan graph in that sense is more similar to the sine graph, because you can imagine this whole graph rotating 180 degrees if you think back to primary school and rotational symmetry. So the tan graph is more similar to the sine graph in the sense that it could rotate around like that. If you're interested about this little part about symmetry here, if something has a reflection where it is the same on the right hand side as it is on the same on the left hand side, we call that an even function. If you've done further maths, I think you may have had this mentioned to you before. This is an even function. And then the sine graph, which we have here, if it has rotational symmetry, we would say that it is an odd function. And so the tan graph is also an example of an odd function. I might tell you a little bit more about that in the future. So the questions you might like to have a go after doing this bit are from exercise 9F. So at this point here, we're going to take a bit of a pause and you can do some questions for me from exercise 9F.